hope you had a wonderful break. We were joking in my class yesterday that we should have a reading week every month. That'd be nice, right? It's not that far-fetched even if you kind of line it up with a long weekend. Anyways, I guess I just want one in March now. We get Easter, but then it's just kind of bogging down our final exam schedule, usually. Oh, before I start this, couple of things. If you started Lab 6 already, it's the one for this week. One, very confusing because we're just introducing it today. Two, but that's okay, you can do it, but might be confusing. Two, I had to fix the code. And so just go back and make sure that the first part is actually correct. It was saying it was correct when it wasn't, and then that was kind of haunting you later on. And so so just if you've started, just go back, make sure that you have the right values in the beginning, and then you're fine. I posted I posted solutions. Now I feel like I have to explain it because I didn't want to write, start at the top, Emily. There were two versions. We're in a tight room, obviously there's two versions. And so I wrote at the top if it was version 1 or version 2. And so they're exactly the same, just different values, okay? And so if you look at the version 1 solutions, for example, blah, 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 blah. Okay. Here, the answers are just very brief, right? And I don't show my work because I'd have to typeset it, and how annoying is that? And so what you can do is go back. I have these full written solutions to an old version, okay? And so in here, I've written out, how I would solve all these problems properly. And so then you can match those values that you had in your version to here. And I had a different tree last year. And so I just kept it in there, but I did say it's a different version just for practice. And so just same problem, different way of asking it. Okay, so you can use that one for practice if you want or not, whatever, doesn't matter to me. And then here, so a little bit of mix and match for you guys, but I trust you can handle it, or you can come ask me. So the tests are yours to keep. I don't want them. I don't care what you do with them. Yeah.
Do you subtract points if you get multiple choice wrong?
A multiple choice wrong? Yeah, one mark each. Did I do it?
Yeah.
Okay. Yeah, if you get multiple choice wrong, it's 1 mark off. Question.
On the email, you had stated that, I guess, if you do well on the exam and this gets, how does that exactly work? Like this is then weighted 0 or?
Yeah. So what I do is once you've written the final exam, because my goal is for you to improve. I don't care about punishing you for you didn't do well on test 1. Anyways, and so that I don't care about that. I care about you improving. Now, so what I do is if your final exam is better, right, then better than one of your tests or the lowest test, I shift that weight. So I make it worth a 0. And then I shift that weight. So now your final exam is not worth 40 anymore. It's worth whatever, 67.5, right? And so now your final exam is worth a lot more, but I care about your final exam. This was just a little pit stop, right? And so, but this prepares you for the final exam, right? And so
like a minimum percentage you have to increase by to get that, or as long as it's even 1% bigger than your.
I just do it, yeah. But I do it sneakily in the back. I download all, and then I write a bunch of if statements, and then I do it. So once, yeah, we're getting out of ourselves here, but once you've written the final exam and I've marked it, then I adjust your grades, and then I send out an email saying, hey, so you'll have your proper grade that you should get, and then if there's been changes, I post those grades, and that's what I'm gonna submit. Okay. So I do make those changes, but of course, I can't make that change until you've written the final exam. Okay, let's see here. And I think I also said, if you want to get ahead, you can read chapter 5, kind of wade through it. But I also hope that you had a nice reading break. So a little bit of reading on reading break might be nice. Okay, was there anything else that I was going to say kind of admin wise? I think we're okay. So if you have questions about your test, let me know. Maybe after class. Okay. Wait. I can see stuff at the top there, but you can't there. Today we're going to start chapter 5, which is kind of the beginning of my favorite part of the course. Everything's kind of been kind of weird and all over the place. Yes.
Is this week 7?
So these slides are all, I put them at the top under slides, and chapter 5 is there. I just have old ones that I haven't cleaned up there. They're hidden. I hope they're hidden, or else that'd be confusing. So we're starting kind of the meat and potatoes of statistics. The reason you have to take this course is for inference. Okay, so chapter 5, 6, and 7, but we'll start in chapter 5, obviously. We talk about inference. Maybe what I'll do is I'm going to add a page here so I have a little bit more room. How do I, I got lines on here. I don't remember how. Weird. Oh well, I'll fly blind. So at the very, very beginning of the course, what did we do? We spent some time. I feel like I need those lines, but that's okay. And we said, okay, let's take it from the top. A variable, there are two types of variables that we're going to talk about. And just in general, you can survive with just these two variables. They're categorical variables, right? There are categorical variables and there are numerical variables. And so for categorical variables, what's a categorical variable? We said, well, I have categories, I have counts in those categories. We spent time talking about, of those who vote Democrat, how many, I don't know, think the earth is warming, or I don't know, one of those go-to examples, right? And so those are proportions, right? So for categorical data, we generate proportions and we analyze proportions. So here we analyze proportions, potentially more than one. So I'll put the S in brackets. This is where we're going to start, okay, is analyzing a proportion. Hello? Oh. Hey, fun. But how do I mute all? There. You're in your double trouble. I guess that would be convenient. So very clever. Whereas for numerical data, what do we have? We have values, we have measurements. So then we're going to be analyzing the mean, right? And so here we're going to analyze the mean, potentially more than one. How's this all going to go? Well, I could have one proportion, right? And I could compare it to some number, right? And so that's what we're going to do in section or in chapter 5 and 6.1. We're just going to talk about one proportion. We spend a lot of time here because we develop all these rules. Now, when I like to play board games. I say I'm a gamer, but not in the traditional same sense. But I like it because you learn rules and you follow the rules, and then you can play the game. And everyone hates hearing the rules explained, but that's my job, is to explain the rules of the game called inference. But once we learn all those rules, and there are a lot, it is overwhelming and there are a lot of rules, but once we know those rules, we can play any of these games. One sample proportion, we can compare two sample proportions. We can compare more than 3 or more proportions to each other, right? And then we can move into means, because what more could you do there? We're done, right? Well, I could compare a mean to a number. I could compare two means to each other. Or what if I have 3 or more means that I want to compare to each other, right? And so we just apply the same rules to all these different question types, okay? And so we're going to spend a lot of time here with one sample proportion, developing the rules of this game, and then we're going to be able to apply it to all these different question types. So then 6.2, we move into 2 sample proportions. And then 6.3, we have 3 plus proportions. I'm saying analyze generically. That's kind of rude, right? But we'll get there. Okay. And then, so same thing in chapter 7. In 7.1, we're going to have one sample mean that we want to compare to some number, right? In 7.2 and 7.3, no spoilers here. One's a special case. We're going to have 2 sample means. And then in 7.4, although we'll never get there because we'll be running out of time, I know it. I know, not with that attitude, Emily. I know. But we can move on to 3 plus means, but we won't. But you could. Same rules apply. Okay. So here, all of these are going to be, I'm going to call them question types. Okay. And if you're looking at your formula sheet, right? I guess I could pull it up here. Where is it? Yep. Snoop. Okay. Here, we're going to start with one sample proportion. Okay. So, and we're going to work our way nice and slowly through this, right? So nothing to worry about yet. Okay, but nice and slowly. And then you flip to the next page. Then we move into 2 sample proportions. So the type of question that we have determines where we're going to be spending our time on the formula sheet. But once you've decided what type of question you have, then you're stuck there on the formula sheet and nothing else matters. Okay, and so that's why I spend a lot of time talking about what type of question do we have, right? And so we're going to be moving through these types of questions. Oh, that's not today. nice and slowly. Okay, so here I'm going to call these the different types of questions. It's going to be important on test 2. You'll have to determine what type of question it is. And then once you've decided that, then you're on rails. You just follow the formula sheet. Easier said than done. Maybe. Same thing with the final exam, right? You have to decide what type of question I have, and then you just do it. Just do it. Okay. So let's talk about inference. When I said analyze, really what I mean is inference. Just doesn't have that same feel to it, right? But what is inference? Inference is when we take sample information to infer something about the population. So when we take sample information to, I was going to say learn, but I'll put that in brackets instead, and I'll highlight infer, which is really to learn, right? So to infer something about the population. But Emily, isn't that what statistics was? Wasn't that what we just said? Beginning of the course. That's what statistics is. It is. All right. So statistics is inference, and inference is statistics. Yes, it is. And that's why we're here. And that's why I call it the meat and potatoes of this course, and everything that we've been doing so far is just kind of building up to inference. Okay. So let's see here. Anything I'm forgetting? In terms of the inference that we could do, there are really only 2 things that we do. We build confidence intervals and we do hypothesis testing. Okay, and those are the things that we need to learn the rules for. But there's a little bit of work that we need to do to get there. Maybe I'll keep the same. So in terms of inference, the first thing that we can do is a confidence interval. And if you peek at your formula sheet, there's a formula for the confidence interval in each of the question types. So not too bad. But what is a confidence interval? Confidence interval gives us a plausible range for what the population might look like. Okay. I'm being generic because, so I take sample information, like a sample proportion maybe, to learn about the population proportion. Right? Then what if I take 2 sample proportions and I try to use them to compare the populations, the 2 populations that they came from, right? So it applies to many different scenarios, but a confidence interval is builds a plausible range for the parameter. Digging back to that vocab that we had, right? The parameter is what? It's a measurement from the population. So we build a range of plausible values, and there's formulas that we use, but we're trying to capture this, this true value, this population parameter. And then the second thing that we can do is hypothesis testing. Hypothesis testing, you probably have done some sort of hypothesis testing. Even I remember in grade school, you know, if I boil this water, I hypothesize that it will turn into a gas or whatever. If I freeze this water, whatever, many different hypotheses, right? And then we did it and we said, hey, it happened, cool. It's not going to be as fun or like activity fun for us, but we're going to do the same thing, right? And so we're going to hypothesize that our sample came from a population that's centered on 0.5, right? Then I look at my sample proportion and I say, okay, I pulled a sample, should be representative of this population, which is supposedly hypothetically centered on 0.5, but I found that it was 0.4, right? We have to take into account the spread and things like that, right? But how likely is it that you pull the sample proportion of 0.4 from if the population was centered on 0.5? So that we're going to build up to that, obviously. But I think it's nice to have kind of the lay of the land before we get down into the nitty gritty. So test whether a sample reasonably came from the hypothesized population. If I told you that I found a mosquito that was this big, you would say, Emily, that sounds very unlikely. What's your kind of internal process for saying that? You would say, well, I know what mosquitoes look like. They're generally this big. Sure, they're big mosquitoes, little mosquitoes, but even then there's variability, and we kind of internally, we know what type of variability to expect, right? And so we're gonna have formulas for that, obviously, but we already know the mechanism that we're using. And so then you say, well, I know the spread, right, of mosquitoes. So something like this big, what's that? 5 centimeters, 7 centimeters maybe, is very, very unlikely, right? So, and we're going to use that same type of mechanism. In terms of where it's coming, so this is section 5.2, and then we get into 5.3. Okay, so nice and slow. So what's 5.1 all about? Well, that spread, that internal, that gut reaction of the spread, right? That's what 5.1 is developing. And so let's see here. Okay. So any questions before we start? I'll just laid out the rest of the course. So that's overwhelming, I guess. But now we're going to take it back. So ultimately, we use samples to learn about populations, right? And so, and that's the beauty of statistics. We don't need the population. We just need a sample, a representative sample. And we talked about how we get that. How do we get a representative sample? We randomly sample, right? And then we can assume that, well, this thing's representative of this population that I'm interested in. I spent time doing that. And so we're going to be interested in these population parameters. Population parameters, sometimes we just call them parameters, or often because a parameter is from the population. Okay. So, but what we use are the sample, the statistics, right? So S and S. But what I also want to highlight is these sample statistics, we're going to start calling them the point estimates. Okay. So here, the point estimate is our best guess. Okay. And so our best guess at what the parameter might be. Okay. We've collected a sample. I've got my sample proportion and I'm trying to learn about my population proportion. Okay. For example. So now, the problem is that there's this variability. So if I collect a random sample and I find the population or the sample proportion is, I don't know, 0.4, right? I understand that if I release that sample and I recollected a sample, right? Random sample again, completely different, then I would expect my sample proportion to be similar, but not necessarily the same, right? We're expecting them to be centered around the population proportion, but there's variability there. And so that variability is kind of like a buffer, right? We've talked about spread. And so the margin of error is, I think of it as a buffer. How do I, can't write this here. Kind of like a, right, or the spread. There, slash the spread. Okay. I'm skimming it because I feel like it's jumping ahead a little bit too much. But that's okay. Yeah. So just as an example, suppose we randomly sample 1,000 adults from each state in the US. Okay. So each state, I pull a random sample of 1,000 people, adults, I guess, and we want to talk about the sample means of their heights. Okay. Now, do you expect the sample means of those heights? They're all from the same population, US adults, right? But each state is representing one individual sample, okay, or a random sample. So what we might have in our data set is something like this. What if I have a state? I'm just going to start down the coast here at Washington, Oregon, blah, blah, blah. Stop there. Get states. And now we're going to talk about the means just briefly, right? We just said, well, let's focus on proportions. But we also said, okay, there are two different things that we could analyze, right? We could analyze the proportions or we could analyze the means. And so this chapter, we kind of introduce the differences between the two. And in the assignment that I'll post, you get to read all these different scenarios and decide if it's a proportion question or a means question, right? Deciding what type of question you have. In this case, kind of confusingly, we're talking about the sample means. That's okay. I find the means are a little bit easier for us to wrap our heads around anyways. Sample mean, we denote by an X bar. All right. So to denote that I have the mean of Washington State, I can put a little subscript on here, right? And then I have the mean of Oregon. These are all just random samples from US adults. So we expect these all to be similar, right? They're very large samples. So we expect them all to be centered on what? We expect them all to be centered on the population mean height, right? And so here we expect these to be similar, centered on the population mean height. Similar, but not the same, which means that there's going to be some spread. And it's that spread that we're trying to develop in this section. Okay. Let's see here. Just realized I was going to mention something here, but maybe it's okay. So just as an example, we could read an article, right? And there are lots of different statistics in the article, okay? And this is why we spent some time practicing reading those tables, right? Because, and I'm just going to focus on these blue sections, the highlighted sections, but a plurality of the public, so 41%, believes that young adults rather than middle-aged or older adults are having the toughest times in today's economy. Now, what's the key here? This is of the public. So the population that I'm drawing from, right, my sample statistic is 41%. And so we've seen this before, right? Of this group, 41%, blah, 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 blah. Right? Whereas later, they introduce among all 18 to 34-year-olds. So now we're in a subgroup, right? And I have beef with fully half. Please don't ever write that. That's so weird. And then follow it up with 49%. Fully half, 49%. Oh man, let's say approximately half. What's so funny is this is actually from Pew Research, and they're a very well-established research group. And so I don't know how they got away with that, but maybe it's just like a thing that they use, but just irksome. Anyways, so now we have a subgroup, 18 to 34-year-olds, and we have an estimate from that subgroup. Cool. We have our best guess at what represents the population of that subgroup, right? And so here, I'll underline this part. Yeah. And then the rest I'll kind of ignore. There's a lot of statistics in there that we could talk about, but let's just focus on these. Okay, so we know that even if we focus on this subgroup, the 18 to 34-year-olds, we know that the population proportion that feels this way, taking a job they didn't want just to pay the bills, is not exactly 49%. But we expect it to be our best guess, right? 49% is our best guess. But we also expect some spread there, right? And so often that's reported as the margin of error. So kind of skipping ahead here, the margin of sampling error is plus or minus 2.9 percentage points for results based on the total sample, right? And so that's what applies as the spread to that first value, the 41%. I think it was 49, yeah. So here, for results based on the total sample, right? So that's the spread, the 2.9% is the spread that we use if it was for all adults, right? Or everyone in the sample. Whereas the spread for the adults aged 18 to 34 was 4.4%. So we have a wider buffer, a wider range, more spread, right? So what we can say, kind of jumping ahead, is we can build a confidence interval. Kind of speeding up a little bit, we're going to take it back, but it's good to have seen it. Say this 95% confidence level is going to go back to the 68, 95, 99.7 rule, right? But we're going to rein it in a little bit. So 41% plus minus 2.9%. Okay. And so what we can say just taking it as a fact that this is for a 95% confidence level, we're 95% confident that 38.1, which is what? It's 41 minus 2.9, so we have to go down a little, and then 41 plus 2.9 to 43.9. Okay, so we just kind of, we take our best guess, our point estimate, and then we go down a little, up a little, the same little, of the public believe young adults rather than middle-aged or older adults are having the toughest time in today's economy. Okay, and so we're going to build confidence intervals. And so now, what are we really saying here? I'm 95% confident that the true population proportion of the public that believe young adults, blah, 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 is somewhere in here, right? Is captured by this interval. Okay. And we can do the same thing for the 18 to 34-year-olds with their spread, right? The 4.4%. We use confidence intervals often, but we don't call them confidence intervals, right? So I live downtown and you ask me, let's see if you care. How far is it to your place, Emily? Oh, it's I give it my best guess, 5 kilometers. Oh, okay, cool. But we know it's not exactly 5 kilometers. That's my best guess. So what do? I follow it up with plus minus 1 kilometer. Quite wide bounds, right? How confident are you? I'm 99% confident, right? That I've captured the actual distance to my place, right? The actual distance from this point to my place, that it exists. That's the population parameter, right? So it exists, it's a real thing, but we don't need to actually go measure it, right? I can give you my best guess, my point estimate, and then I can put some buffers on there and I can attach a confidence to that. What would I have to do to be 100% confident? I'd have to build my bounds so wide that it's not useful information anymore, right? What could I do at 5 kilometers, plus minus 10 kilometers? Well, that doesn't tell me anything. That's useless. So there's a trade-off between how confident you are and precision, but we'll talk about that. But the default confidence level is 95%, just as a spoiler alert. So suppose the proportion of American adults who support the expansion of solar energy is 0.88. Now, what we're doing here is quite common. In fact, I did it in the lab this week as well. Okay, we're assuming that we have this population and we're just going to reverse engineer the formulas that we're going to use. And then we're going to say, well, I saw it in action. I trust that that's the case. And then we can just apply it, right? And so here, just as a note, what this means is we're pretending to know the population proportion, which means what? It means I have the entire population. Okay. And so this is our parameter of interest. So what we can do is we can say, okay, if I know what the population looks like, then let's say I randomly select an American adult. Are they more or less likely to support the expansion of solar energy? Well, I know that the proportion who support it is 0.88, just in general. So I know that the probability of randomly selecting an adult who supports it is 88% or 0.88, right? So just from that, I know that they're more likely to support it. So here, more likely, since the probability is 0.88, we're told. quick reminder, might have been a while. All those 3 P's are all the same. Proportions, probabilities, percentages, sort of, right? Just multiply by 100. And so here, recall that a proportion is a probability, which is almost a percentage, as long as you multiply by 100. Or divide, I guess, if you're moving the other way. Right, so these 3 P's all mean the same thing. So we have this idea of inference, and we said, okay, I'm gonna use my point estimate, so my best guess. Let's see here. So my statistic, my sample information for a proportion versus the parameter that I'm trying to guess what it might be or try to figure out what it might be for a proportion. We use p hat. So p with a hat on top is a sample proportion. So that's what we denote for the sample proportion. We've got a p hat. There's a cute little footnote in the textbook. You're probably too young, but there was a pH vat, which is like a cool thing. And then she says, just like this textbook. Anyways, p hat. And the thing that we're trying to guess, right? I know your gut is saying, oh, well, a parameter has got to be a Greek letter, right? Correct. But this is the one case where I don't use a Greek letter typically, because the parameter, what would a p be? Well, it should be pi, right? Obviously. Maybe I should draw a better pi there, right? So the Greek letter pi, but pi is also a constant, 3.4, blah, blah, blah. And so I tend not to use it in this case, okay? So, but I use just a lowercase p, right? To avoid confusion mostly. Now you're obviously welcome to use pi if you'd like, but in all the problems that we're going to see, I'm going to use p. Okay? And so this is the one time to avoid confusion. So it's the one time that I don't use a Greek letter for a parameter, but in general, we will. Okay. So then, if I were to recap inference, right, in general, let's take it back. So then inference, knowing this, having this terminology, is using p hat to learn about p. Oh, that looks like a capital P, I guess. Trying to learn about P, but so that's what inference is going to be. So my p hat is my best guess, my point estimate, and then I'm trying to use that to learn about P. This slide is just a mess. So now you don't have access to the population. There. The population of all American adults, that seems unlikely anyways, right? And you want to estimate the proportion of American adults who support solar power expansion. What can you do? You can take a sample, you can collect a random sample of American adults and use your sample proportion as the best guess for this unknown population proportion. So we're going to, in just kind of in theory, reverse engineer this thing. And so you're going to sample 1,000 American adults from the population of American adults, right? And then record whether they support solar expansion or not. Or solar expansion, how exciting. No, solar power expansion. Yeah, just a hot mess here, there. So now you have a sample of support, not support, support, not support, right? And what we're doing is we're assuming in this scenario that I have the entire population and we've just collected a subset of those, right? 1,000. You're expecting the sample proportion from that 1,000 to be close to 0.88 because we said we're going to force the population proportion to be that. So it's going to be close to 0.88, but not exactly 0.88. So you find the sample proportion and then you repeat that many, many times, okay? And so this is what I'm gonna get you to do in the lab this week is at first I give you the entire population. You can calculate things like the population proportion, and then I get you to use the sampling function in Excel to pull a random sample. And now you have a sample proportion that you can compare to your population proportion, right? Which is pretty rare that you can see that. And then I give you a break and I say, well, I did that 100 times. Now let's look at the distribution of these proportions, these sample proportions. You can ignore this. This is our code, but you can ignore it. It's just for fun if you want it. We don't use R in this course, but it's a statistical programming language. And it's pretty fun. So what we arrive at is this sampling distribution. This is going to be the distribution of all those p hats. Right now I have a sample of p hats. So it's going to be the distribution of the sample of p hats. Not a good hat. Hey, hey, hey. What's exciting here? Maybe just for me. The normal distribution. Wow. What does that mean? Well, we already know how to do a lot of things with the normal distribution. Okay. We know how to find probabilities associated with the normal distribution, and that's what we're going to leverage a lot, right? We can calculate z-scores, we can use the z-table or software to find those probabilities, okay? And so that's what we're going to be leveraging a lot of. This is called, how this turns into the normal distribution is called the central limit theorem. It's this phenomenon that we're going to be using, okay? And so, but here we just see that that is actually what happens is we get this normal distribution, right? So here it's approximately normal. Whee, which makes us happy, right? And so, because now this, we know, now this is kind of a, remember, we're reverse engineering. We know that the population proportion is 0.88. It's going to be centered on the population proportion. Then we know there's some variability around there, right? Which we're going to find a formula for, right? That spread. But it's going to be centered on the population proportion. Okay, and so now, if I told you that, hey, I collected another random sample of 1,000 adults, and I found a sample proportion of 0.89, right? Then what would you do? And I would say, is that weird? Obviously, we're going to have better terminology than is that weird, right? But is that what you would expect, right? Does it come from this same population or does it come from a different population, right? Is my hypothesis. So then you would say, no, well, 0.89 is somewhere, let's say here on this number line. That's not weird, right? That's kind of in the bulk of the data. That's the probability of seeing that is quite high, right? And so that's fine. That's not weird. Then I come back, I say, oh, forget that. I found a sample proportion of 0.7. Is that weird? Well, if you look at this number line here, right, 0.7 would be somewhere way out here, right? For simplicity's sake, let's just put it here. Put her there. So then you would say, oh, actually, that is kind of weird. That's unlikely. Still possible. Why? Because those tails go to infinity. It's still possible, but very, very unlikely, right? And so you're leveraging, you don't think about it, but you are leveraging that probability, that area in the tail, right? And so then you would say, oh, that's unlikely. Unlikely what? It's unlikely that it came from a population centered on 0.88, right? It's more likely that it came from some other population, right? And there, hypothesis testing done. No, we'll do it nice and slow, but that's it in a nutshell. Okay. And so I guess these slides go a little bit slower, but we said it's approximately normal. What's the shape of the distribution? We also already said the center should be at the population proportion of 0.8, which we've forced, right? And so I'm going to skip this. And what I want to talk about is really the spread. Okay. Blah, blah, blah. So here, they're just reining it in because we're never actually going to have the population. But what we see is going to happen as long as some conditions are met. And so we have to check those conditions. But after that, we can assume that the central limit theorem applies. Now, it's just as important as it sounds, right? And this is what lets us use the normal distribution. This lets us use the normal distribution to find probabilities. That's useful. Now, the central limit theorem, there's a lot of kind of background theory, of course. And so I am going to kind of whiz through it and then show you what we do instead. But the central limit theorem says for one sample proportions is that sample proportions will be nearly normally distributed with a mean equal to the population proportion, which is what we saw, right? We said, hey, what if I know the population? What's it going to look like? And then that's always the case. And that's this central limit theorem phenomenon or theorem. Haha. So it's going to be centered on P with a standard error equal to the square root of P times 1 minus P over N. We'll kind of accept that as fact, if you will. Please. So now we can say that P hat follows a normal distribution centered on P with a spread with a standard deviation of the square root of P times 1 minus P over N. We call it the standard error because it's the standard deviation of the sample proportions. And so it gets kind of boggy. And so we call it a standard error instead. Okay. And so here, we're not going to talk about why this standard error is what it is. We just accept it. That's totally fine. Okay. I tell you, it's totally fine. But I do want to talk about the standard error. So here first, it's abbreviated standard error. So the standard error is the standard deviation of the distribution of p-hats. This is a theoretical distribution, so it gets kind of weird, of the distribution of p-hats. One of the things to notice is what happens as you increase your sample size. As you increase your sample size, you're dividing by a larger number, right? And so P is held steady because it's just the population proportion. It's not going to change. 1 minus P, well, that's also steady. And the square root doesn't do anything. So the only thing that's fluctuating here is the N. So if I increase my sample size, I'm going to be dividing by a bigger number, which means I'm taking the square root of a smaller number, right? And so then my standard error or my spread gets smaller, right? And so we all know, oh, we need a big sample size. We should have larger sample sizes, increase your sample size. We're all familiar with that, but this is the reason, right? The reason is, and it's intuitive, right? The spread becomes smaller and smaller. And why is it intuitive? Because as you increase your sample size, you become more and more, or you get closer and closer to your population size, and therefore the population proportion in this case. Okay, and so here, I'll just say that this is the spread, right? And so the spread gets smaller and smaller. So our estimate, our point estimate, right? We can get a smaller and smaller spread around our point estimate. And that's a good thing, right? Then we're honing in on the parameter that we're interested in. Okay, so there are a couple of conditions that have to be met. Okay, and I find that checking the conditions uses up a lot of brain space, but it's not worth any marks. Uh-oh. Wow. It was worth very, very little marks. And so what I'm going to do on test 2 and the final exam is it's just going to be check boxes, and you have to check the appropriate ones instead of writing out all these conditions, because it can take half a page sometimes, right? And so for us, we just have to have a good idea of what the conditions are, and then we can move on with our lives. The reason I'm not too concerned about it is because they'll always check out, right? I'm not going to make you do a question where the conditions aren't met, right? Because then we shouldn't, right? And so often I'll call these conditions the assumptions. Okay, so conditions or assumptions that we have to check before we can go ahead and assume the central limit theorem applies. So the first thing that we're going to check is independence. Are the sampled observations independent? That's hard to know, right? And so the key thing that I want you to remember is that, well, the way that we can assume that we have independent observations is from random sampling. Most commonly, the question says a random sample of 900 adults was collected, blah, 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 and then it's just stated there, right? So then you have a random sample. Even if it doesn't, what would you have to say? you'd have to say, I assume the sample was randomly selected, right? And so that's why you're checking the conditions or stating your assumptions, right? And so we might have to say, so either stated or we say we assume the sample was randomly selected. Right? Sure. I assume that. All right. So the key thing to remember is the random sampling. That's always going to be a condition for all the inference that we do. Okay. And so just lock that in and you're good. Now this next one is a little bit counterintuitive. And so for that reason, I rarely check it. Okay. And so we said we want big samples, right? Big samples, we're all trained, larger the better. Well, but not bigger than 10% of the population, right? So big is good, but not too big. And that's why I don't really like this condition, because it can be counterintuitive, right? But what happens if you have sampled too much of the population? All of a sudden you lose independence, right? You're sampling siblings, for example, and you're sampling coworkers, depending on what you're interested in, right? All of a sudden you're introducing non-independent observations. And so I'll say I often skip this one. So you can too. So that means, obviously, I skip it. You have to do it though. No, it's not going to be on my list of things, so don't worry about it. But it is kind of a funny thought, right? Big samples, yes, but not too big. Not more than 10% of the population. How about the next one? Now, the next one is going to be very familiar from the normal approximation to the binomial. Oh, right, that old thing. Right, Emily. This is the sample size condition, or later I'm going to call it the normality condition. It's the reason we can assume normality, and so it hinges on the sample size. There should be at least 10 expected successes. Uh-oh, that sounds exactly like the normal approximation to the binomial. Well, it's the same thing, right? And so here, 10 expected successes is really saying that n times p has to be greater than or equal to 10. And I also have to have at least 10 expected failures, right? And I use n times q has to be greater than or equal to 10. And there's a note on your formula sheet where q is 1 minus p. But look at all those keystrokes that I'm saving myself. Q instead of 1 minus p. Just as a side note, what would q hat be then? Probably 1 minus p hat. Eventually, we're going to have a q star. Well, that's going to be 1 minus p star, whatever that is, right? And so it's always just the opposite of whatever the q is, or the p is, I guess. Okay. And so I use q. You're welcome to use 1 minus p if it makes more sense to you, but I'm lazy, so I don't. Now, p is the population proportion, which we just established we don't have, right? And so, right, we don't have the population proportion. And so in that case, we looked for the observed successes and the observed failures to be at least 10. So the observed successes is denoted by a capital X, which we've seen in the binomial as well. X is the number of successes, which means what? Which means that P hat is X over N, right? That's your sample proportion. The number of successes over your total sample size is your P hat. So if you have P hat and N, you can solve for X, right? Or if you have X and N, you can find P hat. So there's very little information that you need to solve these problems. And the number of failures has to be N minus X, which also has to be, I guess both of these have to be greater than or equal to 10. That just means that the smallest possible sample size that you could have is 10 successes and 10 failures, right? So 20. But usually we're trying to detect more or a different proportion than a 50-50 split, which means that we need to change our sample size to be able to detect those small probabilities. For example, if I said we are trying to collect a sample to detect this very rare disease, let's say, and you say, oh, sure, just collect a sample of 20 and get back to me. You'd say, oh, that doesn't really, are you going to be able to detect anything? No, right? Because the probability or the P that you're trying to detect is too small. So you need to compensate for that by collecting a large sample, right? And that's all central limit theorem. Okay, that's all central limit theorem. And so, but that's what it hinges on. And there's a graphic. I thought it was on the next slide, but it's not. That's okay. Let me just, it's on the 2 slides away. That's okay. So what happens is, okay, we've got the central limit theorem. We don't really know or honestly care about what it does, except it gives us the normal distribution. Okay, and so we have checked the conditions, make sure that they're all greater than 10. Good, that's always going to pass, but just something we have to, a hoop we have to jump through. And then we find this problem, right? We said the standard error is the spread. That's cool, but I don't know what P is. So then what do? I can use my best guess at what P is, right? My point estimate. And so then what happens is the standard error of P hat, I put a little P hat on the bottom just to indicate that it's of P hat. You don't have to, but because we're going to introduce standard errors of other things, right? It helps to kind of indicate that this is the one for P hat, is the square root of P hat Q hat over N. Again, where Q hat is 1 minus P hat, right? So I don't have P, so my go-to move is going to be, I'm actually just going to use my best guess, my P hat, right? Okay. Oh yeah. So here, what happens if the NP or N times 1 minus P is small? Now that's the same scenario, right? We're trying to detect this rare thing. We know that, okay, I'm going to need to collect a huge sample. And the reason is because I need to meet this condition. If we don't meet the condition, it's quite skewed, which means we can't use the normal distribution. We have a hard time finding probabilities. We can, but not in this course. Okay, and so just to have a look and see what the behavior is, right? If P is 0.1, so the probability of success is 0.1, then if I have a sample of size 10, this distribution is quite skewed. And so I have to increase the sample size to, let's say, 50 starts looking approximately normal, definitely at 100. right? And so, and at 250, it's absolutely normally distributed. And so moving to a 50-50 split, what happens is it's almost immediately normally distributed, right? So the closer you are to 0.5, the smaller of a sample size that you'll need, but we can handle any of them as long as we check those conditions, okay? Who cares about when they're not met? Because they're always going to be met in this course. Obviously, if you're doing actual research, come back to this, but generally they're always met. So where am I? Oh, look at me go. Okay. So there's a central limit theorem for all the statistics that we're going to talk about. Okay, and so what I want to do, instead of starting confidence intervals, maybe I just want to, hey, it's all glitchy. Add a page. Just want to bring in this section of our formula sheet. So here we are. We've worked through a decent chunk of the formula sheet, I think, right? We've worked our way through newspaper style, and then now we're here at this one sample proportion. We're gonna work through this section nice and slowly, nothing crazy. But then just have a look. We've got a confidence interval formula for P, so the parameter that I'm trying to estimate. I can do a hypothesis test. We don't know what that is yet, but I can do a hypothesis test. We do a fun little sample size calculation in here, but then we don't do it again. Then I can do 2 sample proportions. Well, I can build a confidence interval. I can do a hypothesis test and so on and so forth. So deciding what type of question we have is going to be really useful. So I want to bring in the, hey, formula sheet here. Now, on your formula sheet, you can kind of, I have the theory for the central limit theorem on here. You're not going to use this. This just says that as long as the conditions are met, then P hat follows a normal distribution centered on P with, in theory, a spread of the square root of PQ over N. Right? This is just theoretical, so you can ignore it. It's what we're using, but not how we're using it, right? And so, hey, look, this looks familiar though, kind of skipping ahead. The square root of P hat Q hat over N, okay, nice. Hey, what's this? This is my point estimate, P hat, right? That's my best guess. And what does this look like? Well, it looks like a buffer. It looks like a margin of error. We'll parking lot this, the Z star, but think about the 68, 95, 99.7 rule. If I want to be 95% confident, how many standard errors would I have to move out? 2, right? So we already know how to build a confidence interval, and no, we're still going to do it obviously on Thursday, but just something to think about. And let's see here. The rest of the slide, I think there's nothing left, which is good because I have nothing left. So on Thursday, we'll start confidence intervals. And if you have any questions, let me know. Otherwise, I'll see you then. And I'll stop this.